All right, folks, I think it's time to get started. I hope you can all see and hear me. Welcome back to the Zoom. As I said, I'm going to do a bunch of examples, and then if we have time, we can do the usual breakout groups thing at the end. Because I know people don't really like the breakout groups. Before we get going though, I did grade your tests. So if you go to Gradescope, hopefully you'll be able to see your grades for the test. So go check them out. And as I said last time, I would be happy to sit down and go over it with anybody if you want to go through in detail. I put some comments, but I don't know, it's hard to, sometimes that's not good enough. So I would be happy to go through any of those ones with you all. I have not yet, but I'm going to put my own solutions to the tests on the website too, so you can check that out also. Are there any questions about that? Probably not. But. All right, please let me know if you want to go over the test. I would be happy to do it. And I hope that you got my email this morning. I apologize for messing up, and I didn't notice. I uploaded that video, like months ago, and I just noticed today that I uploaded the wrong video, but put the wrong title on it or whatever. Anyway, it's all fixed now. I hope that you didn't waste a lot of time. If you watched the old one, the messed up one, it was just next week's video accidentally mislabeled. Anyway, everything's better now. Okay, I want to do some examples of the topics for this week. I thought maybe we could just use one example here. This is one function, x cubed minus 12x, and I'm going to try to do the various things from each of the three different sections to this function. All right. The first section has to do with the higher derivatives. There's the derivative we've always been talking about is actually just the first derivative. There's also the second derivative, which means you just take the derivative twice. And there's the third derivative, etc. The higher derivatives are used for concavity. So let's see if we can do this one. So first, I'm going to do three separate questions concerning this one example. First question is, let's find intervals where it's concave up and concave down. On a picture, this looks like sort of the smiley shape versus the frowny shape. If you had a picture of this function, I'm just going to make up a picture over here that looks, say, like this, maybe. The concave up sections are the sections that vaguely have like this U sort of smiley shape, which would be something like here, actually continuing up forever there, something like here. These are concave up. Concave down would be the other way around, this kind of shape. This frowny shape is like that, right? This is concave down. And then the points in between an up section and a down section, there's a single point where it switches from being up to down, and the name for that would be like this point or this point on my picture here. These are called inflection points. All right. Anyway, that was just an example picture. Let's do this real example here. Find intervals where this function is concave up and also concave down. So what do? The concavity, whether it be up or down, is determined by the sign of the second derivative. So I'm going to, first step is to find the second derivative, and in order to find the second derivative, you've got to find the first derivative. So it's going to be, the derivative here is 3x squared minus 12. And then I take the derivative again, and I get 6x. That's it, 6x, right? The 12 goes away. We want to know when is the second derivative positive versus negative. To do that, we make a little chart as we usually do, but this time it's going to be a chart involving the second derivative, not the first derivative. So I'm going to set this equal to 0. 6x equals 0, solve for x, I get x equals 0. And then I also say when this does not exist, but this one always exists. Remember, for the dne part, you're looking for like denominator equals 0, but this thing, the second derivative, has no denominator, so I'll just say NA. Anyway, that means my chart has only one number on it. 0, x equals 0 is my number where the second derivative is 0. Sorry about that. So I put 6 just because I saw a 6 on the page, but it's not 6. The second derivative is 0 right there. And then I do the thing with the plug numbers in to the left and to the right. Now, I'm not going to use the same numbers I just tried because I'm not. I'm going to use -1 and +1, right? Those are numbers to the left and to the right of 0. And I plug them into the second derivative. So f double prime of -1 will be 6 times -1 is -6, which is negative. So it's negative on the left side. And then f double prime of 1 is 6 times 1, which is, what? The other one was -6. This one is +6. I said it right, but I wrote it wrong. So I got a plus on that side over there. All right. This is the chart for the second derivative, and at this point we can say what the answer is. Remember, the question I've been trying to answer is, give me intervals where the thing is concave up versus concave down. So I'm just going to say it is concave up on the interval 0 to infinity. That's over here, right? The right side, which is where the second derivative is positive. And then on the other side is concave down. Concave down on the interval -infinity to 0, like that. All right. I didn't ask at the beginning, but we might as well ask, are there any inflection points of this function? Remember, inflection point are the points on the graph right in the middle, in between where it changes from being negative to positive. And so we can see here, actually, x equals 0 is an inflection point, because x equals 0 is where it changes from being concave down to concave up. That's called an inflection point, when the concavity changes from one sign to the other. All right. Anybody got any questions about that one? Sorry, I messed it up. I ended up all right.
Okay. I have a question.
Yes.
So, sorry, just so I have this correct, the inflection points are, it could be from negative to positive or positive to negative.
Yeah, that's right. It's just where the concavity changes sign.
Okay, thank you.
Minus to plus or plus to minus. Yeah. Thanks. Okay, great. So that was the first question I wanted to do concerning this example. You know, this was vaguely like the first section of the homeworks, are all about concavity, concave up, down, and inflection points. The next section concerns the second derivative test. And this is a method for finding and identifying the extrema using the second derivative rather than the first derivative. Now, you do have to use the first derivative as part of it, but you don't have to make the chart. So let's try. Here is same function, but our job is different this time. Let's find and identify the relative extrema of this function. F of x equals, I want the same function. It was x cubed minus 12x. All right. And I'm going to say using the second derivative test. Now, we already know a method for doing this from last week. That other method is called the first derivative test. That is, you make the chart of the first derivative signs, and then you say when it goes from plus to minus, that means it's a maximum, and when it goes from minus to plus, that means it's a minimum. All of that was called the first derivative test. Let's try and do it using the second derivative test. They are just two different methods for accomplishing the same thing. If I just ask you to find the relative extrema and don't say which, then it's up to you to choose, like on our test or something. You can do it either way. Unless I specifically tell you to do one way or the other, then you do the way I told you. Using the second derivative test, how we do it, first we find the critical numbers and then plug them in to the second derivative. All right. The critical numbers, remember, are the places where the first derivative is 0 or does not exist. So this second derivative test does still involve the first derivative. Anyway, let's see if we can do it. First of all, find the critical numbers. Let's do that. I take the derivative, and I'm going to set it equal to 0. So the derivative, as we know already, is 3x squared minus 12. To find the critical numbers, we set that equal to 0, right? And we also say when it does not exist, but that doesn't matter in this example. The critical numbers would be, I am setting, actually before I do that, can I simplify here? We could factor 3 out, and what remains is x squared minus 4. Can anybody know how to factor x squared minus 4? Somebody shout it out.
X plus 2x minus 2.
X plus 2x minus 2. Thank you for shouting. Make your voice heard. Don't forget to vote. I already voted. I voted, but I didn't get the sticker because I did it by mail. It's a scam, I tells you. I like the sticker. Okay, the critical numbers, we set this derivative equal to 0. So I go 3, x plus 2, x minus 2 equals 0. The 3 has no effect. Here's something that I saw people messing up on the test and on the homeworks. Some people think the 3 makes it so like x equals 3 is a critical number. That's not so. This 3 out here has no relevance because you can immediately divide it out on both sides of the equation. And the right-hand side will just say 0 divided by 3, which is still 0. This is the same as this. The 3 has no effect. If it were 3x, then that matters, because then you would separately set 3x equal to 0. But just a constant in front there doesn't matter at all. Anyway, I get x, you split it up like this, right? We've all done this many times. X equal minus 2, x equal plus 2. These are the critical numbers, okay? And remember I said the method for doing the second derivative test, you find the critical numbers, I just did, and you plug them in to f double prime of x, the second derivative. This says f double prime. So plug those two numbers into f double prime. First of all, I have to find f double prime. It comes from taking the derivative again right here. It is 6x, right? We did that in the previous example. And now I'm going to plug the critical numbers in to f double prime. So plug critical numbers into f double prime. What do we get? I got f double prime of minus 2 is the first one. As usual, we don't care so much what the number is precisely. It just matters if it's positive or negative. But in this case, we might as well just compute it. It's 6 times negative 2, right? It's simple enough. And then that's a negative 12. This is negative. So that means x equal minus 2 is a relative. And this one, here you just have to remember how to do the second derivative test. When the second derivative is negative, anybody remember? Does that mean it's a maximum or a minimum?
Maximum.
It is a maximum. Thank you for shouting it out. When the second derivative is negative, it is a maximum. That's because a second derivative being negative means the shape is like this, right? It's a downsy, a frowny shape. That kind of shape, right? Which means your point is a maximum. Okay, and what about the other one? F double prime of positive 2. I got 6 times positive 2, which is positive 12. This is positive. So that means the shape is concave up, which has this smiley shape, which means that point is a minimum. So x equal 2 is a relative minimum. This is the second derivative test. All right. In some cases, it's preferable to the first, better than the first derivative test because you don't have to do any charts to find whether it's a maximum or minimum. Usually it's not remarkably easier or harder than the first derivative test. Any questions about that one? All right, and the last type of question that you're going to see on this homework is concerning curve sketching. This is the most elaborate ones in my opinion. Let's try to draw the graph of this same old function, f of x equals x cubed minus 12x. And this is the video that I messed up. It was uploaded in the wrong spot. So if you haven't watched this video yet, that might be why. Or maybe you just haven't watched them yet. I don't know. Draw the graph. This is the section on curve sketching. It turns out all this business about the derivatives and the critical numbers and the increasing, decreasing, everything can be used to draw the graph of a function, even if you don't, without using a calculator or a computer or anything. Anyway, what are the various steps here is going to be something like find the critical numbers and the increasing, decreasing chart. We know how to do all of that stuff. And then plot the critical numbers. Your goal is to draw the graph of this function. So actually plot them with their x and y values. And then I will say connect the dots. And you'll see what I mean by that in a moment. All right. Let's see if we can do it. So I am going to start by finding the critical numbers. So in order to do that, I find the derivative. It is 3x squared minus 12, as we've done before. And to find the critical numbers, actually, we already did that in the previous step. Would you mind if I just said the, well, since we need the chart anyway, we might as well work this out. We get 3, when I'm simplifying here, 3 times x squared minus 4, and this you can factor as x plus 2x minus 2, like so. All right, and then the critical numbers, just like before, we already did this, x equals 2, x equal minus 2. So one thing that we did not do in either of the other two problems was the increasing and decreasing chart. Let's do that. So the increasing, decreasing looks like I put plus 2 and minus 2 on here. All right, I sneezed. I got symptoms. No, I don't really. I have seasonal allergy symptoms. Don't worry, I'll be fine. Doing the increasing, decreasing. The first derivative is 0 at these 2 points because they're the critical numbers. What about in between? Is it positive or negative? We got to do this thing. We know how to do this, right? So I plug in, say, a point all the way on the left. Let's use negative 3. F prime of negative 3. This is 3 times negative 3 plus 2 times negative 3 minus 2. This is a positive times a negative times a negative, isn't it? Those two things are both negative. And so it's going to be positive over there. How about in the middle? I'll use 0. 3 times 0 plus 2, 0 minus 2. This is going to be 3, well, positive, positive, negative. So that's negative in the middle. And then finally, let's use 3 on the right side. 3 times 3 plus 2, 3 minus 2. Those are all positive, so this is going to be positive. All right. So I made the increasing, decreasing chart. This doesn't immediately come into play, although once I start trying to draw the graph, this is the principal tool by which you know what the shape of the curves looks like. You do it according to this increasing, decreasing stuff. Let's see. So my general strategy, like I said before, find the critical numbers, do the increasing, decreasing thing, and then plot the critical numbers. That means with their x and y values. So before I begin to draw the graph, I need to find the y values for the critical numbers. Y values for the critical numbers. They are, of course, x equal 2 and x equal minus 2, right? I want their y values. To find the y values, you plug them into the original function. You know, y equals f of x. So I'm going to do f of 2 and f of minus 2. You got to keep it straight, and it can be confusing in a problem like this. Keep it straight what you're going to plug this into. Not the derivative, but plug into the original function here, because I want the y values, all right? And the original function, if you recall, is up there, x cubed minus 12x. So when I plug in f of 2, I get 2 cubed minus 12 times 2. Sometimes you might want to use your calculator to do this step because it really does matter what the number is. It's not the sign that I care about. I care about the number. 2 cubed, it should say there, not 2 squared. If I give you one of these on a test, I will make it so these numbers are easy to compute in this step. Anyway, that's 8. 2 cubed is 8 minus 12 times 2 is 24. So it looks like I'm going to get negative 16, right? I think that's right. And then f of negative 2. Okay, let's do it. Negative 2 cubed minus 12 times negative 2. What's that? Negative 2 cubed is negative 8, and then plus 24. And this is plus 16. Okay? So these are the y values, and I'm going to begin my picture by plotting those numbers. So on my graph, this is going to be my answer. You know, the whole question is just to draw the graph. So first of all, I have a number here. A point here is going to be x value 2, y value negative 16, right? And this point here is x value negative 2, y value 16. So let's plot those 2 points on my graph. 2 and negative 16, I'll just write it like this. That point, right? And then negative 2 and positive 16. So back here and up here. How am I doing so far? All right. All right. I'm feeling good. Can you hear me? I hope so. Just to make sure that I remember, these 2 points here, they are the critical numbers, and they are when the derivative is 0. So I'm going to, just to help myself out, I'm going to put a little sort of horizontal flat line there. This is to remind myself that when I eventually draw the curve, it must go horizontally through those 2 points because they are critical numbers where the derivative is 0. So when I draw my curve, it must pass horizontally through those 2 points. All right. Anyway, what was the final step? The final step that I wrote here, find the critical numbers, do the increasing decreasing chart, plot the critical numbers, and lastly, connect the dots. What I mean by that is, I have 2 dots on the picture here. Connect them. Now, there are many ways, of course, that you could draw a line connecting these 2. You could just put a straight line like that. That's not correct. In this example, that graph is a x cubed, whatever, minus 12x is not a straight line, right? So don't draw a straight line. Whatever you draw, it must pass horizontally when it hits those 2 points. And according to my increasing decreasing chart, in between, in this region, from minus 2 to 2, the graph must be decreasing, right? Which, I mean, I suppose it should be decreasing in order to fit this picture. How are you gonna do it? I'm gonna start drawing on the left point. When you come out of this point, you must go straight across horizontally and then immediately start to decrease, finally arriving at the other point also in a horizontal fashion. It must therefore look like this, right? You have to come out of the point on the left horizontally, then decrease, and then enter the point on the right also horizontally, all right? So I'm using the fact that it's decreasing in the middle, always decreasing, like it doesn't go up and down or whatever. No funny business, it just goes down to the other point. Okay, this is not the entire graph. I also need to say, what about over here? There's got to be some part of the curve over here, and then also over here on the left side. And here you have to, there's no other dot to connect to. Let's look at the right-hand side. So as I leave this point down there and traveling to the right, I'm going to begin, like exit this point going horizontally, but then should I go up or down? What do you think? Anybody think you know? Should I go up or down as I move to the right? Anyone want to shout it out? You should be guided by the increasing and decreasing chart. Should I go up or down? I should go up. Yeah, thanks. It's because on the chart it says that the function is increasing to the right of x equals 2. So when I leave this point, I gotta go up like that. All right, it should leave the point going horizontally, but immediately increase like that, and it will continue to increase forever. That's because the chart here says it will be increasing for, you know, all the numbers greater than 2, right? Okay, what about on the left side? Again, I will, as I move to the left, I will exit this point going horizontally, but then it's a question of should it go up or down? Now, the chart about increasing and decreasing says the function is increasing over there. This can be a little confusing. That means it goes up as you move to the right, which means it should look like this. All right? This business here is increasing. I don't know if you thought, because increasing, if you expected me to draw going up as I move to the left, but remember, increasing, decreasing is always measured as you are moving to the right. Is it going up or down? So in this case, increasing means as I move to the right, the thing has to go up until it reaches that point. All right? And that's the graph. You can always, on these, you know, if you're doing this on your homework, you can always check your answer by graphing this function on a computer or a graphing calculator. You should see vaguely this shape.